we're going to do some more advanced problems using the ideal gas law. So in this problem, we're going to calculate the mass of a certain sample of gas. I'm going to use the Hindenburg as the example. Its construction on this was started in 1931. It was a Zeppelin, which is a rigid airship, and that's not the same thing as a blimp. And when they designed it, it was supposed to use helium as its lifting gas. The idea behind a lifting gas is you fill a certain volume with a gas, and if the mass of that gas is less than the mass of the air it displaced, well, it's a lifting gas. Now, at that time period, the U.S. had the main reserves of helium, and they were not exporting that to anybody. So the Germans had to redesign the Hindenburg to use hydrogen gas instead. Hydrogen gas is a great lifting gas. If you take the ratio of the density of air as standard conditions over the density of hydrogen gas at standard conditions, it's more than 14 to 1. You can also make hydrogen gas. You can't make helium that way. We do that all the time in chemistry lab. You throw a little zinc, a little hydrochloric acid, get a little sample of hydrogen gas to use. There you go. There is a problem with hydrogen gas, however. Now, inside the rigid airship, you have these big bags of gas. They're gas cells. And as the Zeppelin rises, the pressure will change inside those gas cells. So if you need to, you can vent a single one or multiple ones if needed, so you can distribute the buoyancy property more effectively. I did say there was a problem with hydrogen gas. You know what it is, right? It's flammable. Germany had been operating hydrogen-filled airships for many years without a single injury until May 6, 1937, at Lakehurst, New Jersey. Now, whether it was through static electricity discharge due to buildup on the outer hull itself, or to when they went to moor it, however it happened, some gas caught on fire. There was a gas leak. It caught on fire, and it quickly spread throughout the hydrogen gas. And that sample of hydrogen gas combusted in less than 2 minutes. I've read that it took approximately 90 seconds to burn that gas up. So that's the problem with using hydrogen gas as your lifting gas. Now, let's figure out the mass of gas inside that Zeppelin under these conditions. First glance at this, you think, mass? Hang on. The ideal gas law deals with pressure, volume, temperature, and the number of moles, not mass. So let's pull the information out and then see what we can do with it. We're told the volume. We're told the temperature. That has to be in Kelvin, not degrees Celsius. And we're told the pressure. Now, even if you don't know how to solve the problem, you should be able to look at this and see that we need the value of R. Those are not changing conditions. They're just conditions given right here, right now. So I'm going to choose the value of R that has the pressure unit of atmospheres in it. Now, maybe we're in trouble. Go back and look at the problem. It says calculate the mass. What we don't know is we don't know how many moles of gas we have. Now, up until this point, we didn't care about the identity of the ideal gas because it didn't play a role in the calculations. If we treat all the gases as ideal, who cares if it's hydrogen or helium or nitrogen or oxygen? Well, in this case, we do care. The identity of the gas was told to you because we need to know something in order to calculate the mass of the gas sample. Because see, the ideal gas law gives you moles. We want mass. And what's your connection between moles and mass? Molar mass. That's the molar mass for hydrogen gas, for H2. All right, still not sure how to work the problem, but at least we should be able to start it. Instead of deriving a mathematical formula that says mass equals with a bunch of variables and then plug in our variables, I'm going to go through and do this using dimensional analysis. So I'll start with the value of r. Now we either multiply by r or we take the reciprocal of r. The gas constant has moles in it, but we want mass. And we already discussed the relationship between mass and moles. It's the molar mass. So whenever you see a problem that says calculate the mass and you're doing an ideal gas law problem, mass is code for moles. Calculate the moles. So I need to take the reciprocal of the gas constant because I want moles in the numerator, not the denominator. Multiply by volume. Multiply by pressure. Unit analysis. Divide by temperature. Now if you look at what we've done so far, the unit we have left is moles. And you could go equals, calculate your moles, and then see what needs to be done next. Or we can just keep going. There's no need to use the equal sign yet. We need the mass, which means we have to use the molar mass. So do you want to go grams over moles or moles over grams when you put the molar mass in there? You need to put it in as grams per mole. One reason, you need mole units to cancel. Another reason, you want grams when you're done, not 1 over grams. We get 3 significant figures when we're done. And it's a pretty large number. 10 to the 7th grams. Wow. Your conceptual check. That number sort of goes past my conceptual check. Because I can't picture 10 to the 7th grams very easily. I know the volume was pretty large, 10 to the 8th liters. You know, this 10 to the 7th grams, if you take, say, people and take an average of 80 kilograms per person, that's over 200 people. That doesn't help. Cars. If you assume that a car is somewhere around 1,000 kilograms, then this is somewhere around 17 cars. On this, really, for your conceptual check, you have to go with your unit analysis. Double check to make sure your units are correct.